Section 6, Expansion Scale Factor, A of t. Now let's catch up on the mathematical physics theory of the expansion of the universe, which actually predated Hubble's 1929 publication. In 1915, Einstein published his general theory of relativity, a very complicated set of equations where the density and pressure of matter and radiation tells space-time how to curve, and space-time curvature tells matter and radiation how to move. The force and acceleration of gravitational attraction is one aspect of curved space-time, as we covered in the course on gravitation and black holes. In 1922, physicist and mathematician Alexander Friedmann solved the general relativity equations to produce the equation that cosmologists still use today to characterize the expansion of the universe. Let's hold off with his equations. Friedmann assumed that the universe consists of a perfect fluid with a density and pressure that can change with time, but at any time have the same value at all points in space and in all directions. This leads to a metric called the Robertson-Walker metric, or the Friedmann-Lemaitre-Robertson-Walker metric, FLRW, which we will not cover in this course. The fluid is assumed to be homogeneous, identical at all locations, and isotropic, identical in all directions. This is believed to be a good approximation for our observable universe on the largest scale, greater than about 200 megaparsecs, about twice the size of galaxy superclusters and galaxy voids, about 0.7% of the diameter of the observable universe, as covered in supplemental video number 4. Though some recent discoveries question this assumption. Friedmann necessarily assumed that general relativity is correct and unchanging in time, and cosmologists assume that the fundamental laws and forces of physics and the properties of elementary particles have remained constant throughout the observable universe from after the Big Bang through today, until there is evidence to the contrary. We will get to Friedmann's equation, but let's get oriented and learn some before getting to that math. Friedmann's assumptions lead to describing the expansion of the universe with a scale factor, A of t. The scale factor describes the increase of far long distances everywhere in the observable universe as a function only of time since the Big Bang. The scale factor is not a function of location in the universe. It is universal, and it supports the cosmological principle. We take the scale factor to equal 0 at the moment of the Big Bang, and equal 1 at the present time, now, when we are observing light arriving from distant galaxies. The scale factor has been increasing since the Big Bang. Not linearly in time, it is a curve. Here is a quick preview of the scale factor over time, the blue curve, that is approximately the 2/3 power of time since the Big Bang. We will examine this in detail later in the course. Let's do an example. Astronomers believe that the galaxy NGC 1399 is 66 million light years from us now, and the scale factor now is 1. About 8 billion years ago, the scale factor was 1/2. And that galaxy would have been half as far from us. 1/2 times 66 is 33 million light years from us 8 billion years ago. So, to calculate some distant galaxy's distance from us at a specific time, t in the past, we multiply its distance from us now, which astronomers figure out, times the universe's expansion scale factor at the desired time in the past, which cosmologists model from all available evidence. There was a time in our observable universe before stars and galaxies had formed. The universe was a pretty uniform gas. The universe was still expanding, but it was the distances between atoms that was increasing with time back then, because the atoms were not bound together or to anything else. We have often said that space is expanding or has expanded. We can visualize space. We can visualize a region of space expanding. But this phrasing raises some natural questions that will only confuse us. Does the old space open up at some places and new space gets inserted? No. Would it be possible to detect a region of new space versus old space? No. Does each point in space carry its own clock showing its age? No. Where does the new space come from? And how does it know to get inserted? No. Just no. These questions are not helpful, so we should stop saying and thinking that real space expands by adding new space. In special relativity and general relativity, times and lengths are dependent on the observer's conditions. In cosmology, large lengths are proportional to the scale factor, increasing since the Big Bang. So, we must stop thinking of space as expanding by adding new space. Also, don't think that expanding space drags galaxies away from each other, or that as galaxies move apart, they drag space along with them. There is no dragging in that sense. Galaxies do co-move with space, but no force is involved. From now on, the right way to think of the expansion of the universe is the universal scale factor A of t, which is the same everywhere in the universe at any time since the Big Bang, assuming the energy density and pressure have always been the same at all locations in the universe at any given time. Here is a beautiful and useful artist visualization of the history of the universe. Time increases left to right. At specific times, a circular hoop is drawn. The radius of the hoop is a loose, qualitative suggestion of the scale factor at the time, so of the expansion of the universe. This helps us to see different epochs and that the distance between distant galaxies has increased over time. But it is not a timeline of individual galaxies, and this is not the actual scale factor. In section 14, we will cover the actual scale factor graph. In subsequent videos, we will cover cosmic inflation, the cosmic microwave background, the dark ages, and the first stars.